Welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with nearly 3,000 people working on a wide array of topics. The computer science department works on applied AI projects for the benefit of society, and we organize these learning machines seminars every week. This meeting will be recorded, and if anyone wants to be removed from this recording, just let us know. Also, make sure to check out the list of interesting talks on our YouTube channel. Today, I have the pleasure to introduce Stefanos Georganos, who is an associate professor at Karlstad University and a researcher at KTH Stockholm. So Stefanos obtained his PhD in 2021 from Université Libre de Brussels on the use of VHREO satellite data for multi-thematic urban mapping of sub-Saharan Africa. His research interests include quantitative human geography, remote sensing, spatial epidemiology, demography, and machine learning. And the topic today is filling the gaps, AI and Earth observation in support of urban sustainability in the global south. With that said, I will hand over the word to you, Stefanos.
Thank you very much for the introduction, Olof. Allow me to share my screen first. I hope that you can get a view of my screen. I am delighted to be here, and I thank you very much for the invite. Please, by all means, you feel free to ask questions during my presentation, but I do know we will have some time after the end of the presentation as well, so just do whatever you feel free. As Olof mentioned, my talk today will be about filling the data gaps in the urban parts of the global south or majority world, and in particular sub-Saharan Africa, using AI and Earth observation. Now myself, I am an urban geographer. I'm not so much of a computer scientist as most of you are probably are. So this presentation will focus mostly on discussing the problems, the synergy between Earth observation and artificial intelligence, and a lot of urban applications, from simpler ones to more complex, which will also reflect the increasing difficulty to tackle specific issues of filling these data gaps and why we need more advanced algorithms to do so. And also some outlook and some discussion points for the future. How does a deep learning, for instance, has to be tailored to address these data gaps? So focusing again on the urban part, why cities? Well, the large parts of the world are heavily urbanized. From 55% currently, by 2050, 2/3 of the world's population will live in urban areas. At the same time, cities consume most of the world's energy resources. They contribute most to the global CO2 emissions from another perspective. And while I would say the large parts of the globe are already heavily urbanized, there is parts that are currently undergoing immense and dramatic transformation. So if we take, for example, sub-Saharan Africa or parts of South Asia, we see that the urbanization is now taking place. They are not too heavily urbanized yet. And this reflects, if we check the bottom figure and the projections we have, reflects on the population growth. So Africa, for instance, the trend is it will keep increasing, while in other parts, it will it's already decreasing or it will stabilize. There we will have a significant increase. We will have a large population growth, and this growth will happen in cities. So talking about cities then, we need a lot of data. We need data regarding where people live, how do they live, how is the infrastructure, what is the profile of the urban residents, in order to deal with the issues that I will talk to in the following slides. And to start with, a large part of the data that we typically acquire, a lot of this information is coming from census. Nonetheless, there is a huge census gap in large parts of the African continent. For instance, in the figure that we see here, it depicts the year that the last census happened. And I think the date is 2020, so it might be some small changes currently. But what we can keep out of it is that there is countries, several countries, that the census has not happened for more than 15 or 20 years. In DRC, for instance, there hasn't been a census for more than 30 years. Even if we have census data, they are often at unsatisfactory level of detail. We see, for example, a census from 2003. It can rapidly change in 2011, different units, different types of information. It is not adequate to tackle the urban transformation and the urban needs of the residents. There is also a lot of spatial data gaps in general amount of information. And I use similar examples usually in my presentation. So this is an image, satellite image, around the area of the RISE Institute in Gothenburg. I suppose I got it right, and it's the one that you're all familiar with, or most of you. And if we use Google Maps, for instance, as the background, we see that most of the buildings, or all of the buildings actually, are covered. We have information about the land use, the street network, the addresses, a lot of things that we know usually help to have. Now, if we move to Ouagadougou, the capital of Burkina Faso, and a part of it, and this is an informal settlement. If we use the similar type of layer, this is what we get. About half of the buildings are missing. There is no information about addresses or land use or land cover information. There is a huge gap there. And this is where a little bit of the Earth observation part and component is jumping in to assist in that. When we talk about urban and dramatic transformation, it's also nice to visualize it a bit more. This is again Ouagadougou. This is a transitional zone between the formal settlements and the informal settlements. And this image is coming from 2002. And then just 8 years after, so in 2010, the whole area has transformed. Within 8 years, we see a massive change on the urban landscape. And we're talking about hundreds of thousands, if not millions of people who are probably arrived there. They rebuild the infrastructures, and the whole landscape, sorry, has changed. But the level of information we can work with is still very limited to sometimes non-existent. So again, going a bit more into the urban infrastructure, of course, what does it mean by talking about the urban transformation? Well, for the so-called global south, which sub-Saharan Africa is part of, so countries where industrial development is not so high and economic inequalities are quite large, what happens is that when the population of these rapidly transforming cities increases, large parts of it ends up in the so-called slums. And right now, more than 1.6 billion people live in these deprived areas or slums. And by 2050, the slums population is expected to grow to more than 3 billion. And that's about 30% of the general projected population of this roughly 10 billion in 2050. In fact, if you take a close look at this figure, there is cities where the majority of the population living in them is in slums. And by slums, if we take the UN definition, it means a household that lacks fundamental amenities and infrastructural amenities and services, access to electricity, enough open space, access to healthcare. So it's a whole set. I mean, it's not a very strictly defined term, but it refers to what we call deprivation and deprived of essential services. So things are not looking too bright in some parts. And what can we do about it? Well, there is, of course, except for local initiatives and the local strategy of these areas, we have international initiatives, well, which we are certainly familiar with, the Sustainable Development Goals. And because we're referring to cities, the Sustainable Development Goal 11, which refers to explicitly to the well-being of the urban residents with clear targets to ensure access for all urban residents to adequate, safe, and affordable housing, to eradicate or upgrade slums, and also to enhance inclusive and sustainable urbanization and participatory capacity in all of the countries that are involved in the Charter. So given that we have a target, we have an objective, how can we help monitor these indicators? How can provide this missing information to allow for practical and evidence-based planning to take place? A lot of it we can get through Earth observation. Now, why is Earth observation very useful for urban monitoring and tackling different urban issues? It has very high temporal resolution. We have thousands of satellites constantly orbiting the Earth, capturing information about its surface. It connects very well with computer vision and AI. We can have algorithms that are used to ingest massive amounts of remote sensing data and Earth observation data. It can provide quite robust outputs, almost in an automatic fashion. And a very crucial component in this is that we can use the combination of Earth observation and machine and deep learning for both biophysical phenomena and for socioeconomic. And why is that? Well, in one sense, the physical components of the surface we can measure. It's easier, it's more simple and more intuitive. Socioeconomic, we can also measure to an extent, of course, because the physical morphology of a city reflects the social processes that have built it. So by just unraveling the physical surface, we get a lot of information about socioeconomic components, and this can reflect poverty, deprivation, even health outcomes to an extent. And we will see examples of that and how they can link with machine and deep learning. So starting with characterizing the urban surface, well, there is a lot of resolutions that we can use remotely sense data to investigate the urban fabric. We can start from Sentinel-2 data, for instance, that are globally and publicly available, and they are at a bit coarser resolution, about 10 meters. We can have more very high resolution satellites, such as Worldview, about 0.5 meter resolution, aerial photos, drones and UAVs, centimeter resolution. And depending on what we use, we can unravel different dimensions and different indicators of the urban surface. So this, of course, depends on the application that we're interested in, the scalability. It's one thing to try to map the whole continent with UAV, and another thing by using Sentinel-2 data, of course. Another factor is the cost benefit of what to use. We can have free of charge data, we can have low cost data, and we can have very expensive, very high resolution data that are really untenable to use for large scale analysis, even though the technology is advancing, and we will hopefully in the next years reach a point where we can use at a massive scale very high resolution data for this type of analysis. So what I'm gonna go through here in this middle part of the presentation is starting from knowing very little things about the urban surface, how far can we go? So we will start from basic information or more fundamental information, more commonly used applications such as the land cover of a city, using machine learning, to reach more complex levels, but refer to epidemiology or to population mapping. So to start with, one of the most fundamental applications in remote sensing that we need to have there is the land cover, and consequently the land use. The land cover refers to the physical components of the surface, while the land use refers to the use of the land assigned to it by people. So starting, for example, here, this is Ouagadougou again. What we see is we have the satellite image, and we use a supervised machine learning classification. Nothing fancy. It could be random forest, it could be XGBoost, simple algorithms, standard and well-known and robust, to map the land cover. Where do we have buildings? Where do we have trees? And this, we can create the label data by using voluntary database such as OpenStreetMaps, or just by labeling ourselves by looking at the image. But then a problem arises at the second step is if we want to go from the land cover to the land use. Typically, the land use refers at a spatial configuration, for example, a parcel, a street block, one would say. And there we did not have such information. You know, in Sweden, you can have the parcels, you can have the street blocks. You can directly skip this step and perform a second classification to go from the land cover to the land use like that. So there we had to also reconstruct the parcels at this intermediate step. We downloaded all of the street network of OpenStreetMaps, and we reconnected it to create the parcels of the city, the street blocks. And from there, we used another classification, supervised classification, to derive the land use. And it was not a simple land use classification, it was quite detailed. We classified different levels of planned neighborhoods, different levels of unplanned neighborhoods, or the so-called informal settlements or slums, and even industrial areas or commercial areas. So immediately, just by starting with a satellite image and some ancillary data and a lot of hard work, we could have some very interesting information about a whole city. This analysis was done at a citywide level for Dakar, in Senegal, for Ouagadougou in Burkina Faso, for Kampala in Uganda, for Dar es Salaam in Tanzania, for a lot of cities. But this information were either very outdated or outright unavailable. And it's very easy. We can very quickly see the differences in the urban fabric, where we have informal settlements and where we have formal, just by looking at both the image and the land cover. What we did to go to the land use again was to go into landscape metrics. This is not so much machine learning, but it's still interesting to know how we can go from one to another. And landscape metrics depict the configuration of the land cover, which gives very useful predictors to the machine learning classifier and infer the land use at the last step. This can be elevation, it can be the diversity of the built-up areas or other land cover classes. They help a lot. Now, as we talked about the general structure of the urban fabric, we were mostly interested in the informal settlements, on the so-called slums. So we're jumping here. We're going to Nairobi, the capital. Yes?
May
Sure.
I jump in? Thank you.
Yeah.
So I was wondering about the difference between land use and land cover, and also how the labeling was done there. I mean, I understand land cover being whatever, you know, the earth produced before humans intervened. But then there is an overlap, like, you know, if you think about the botanical garden and a forest, I mean, it might look very similar from the sky, a botanical garden being produced by humans, whereas a forest is just what it was before. So can you talk a little bit more about the labeling of these and how you know, we differentiate them?
Yes, sure. And this is a very interesting point as well, because it is not easy to just start labeling street blocks once you have the land cover and say, okay, this is informal, this is formal, because in some cases we're quite right, but we are not living there. We're just looking at an image or a couple of images, and we're just having our own biases. So what we did back then is, it was me and another colleague who did an initial labeling. And also we asked two people that are residents there and were collaborating with us to also do labeling. And at the same time, we used a lot of ancillary data from OpenStreetMap. Whatever, it was incomplete, of course, but it could give us some solid training data, because there was some, you know, as you said, it could be a park that was labeled, or that this building is, you know, the parliament, or it was a factory.
Right.
And then we put all of them together and we checked the consistency of our labeling. So we kept what we have, let's say we had solid degrees of agreement, all of us together. And then we got a, you know, small but robust training data set to work with. And if I'm not mistaken, the accuracies were at a range of about 80%. So not too bad, but, you know, not perfect either, of course.
Okay. Okay, thank you very much.
Yes, so as I was saying, now we're moving to Nairobi, and our focus there was mostly on the deprived areas or the slums, not really focusing too much on the whole urban fabric. Now, deprived urban areas are very diverse by themselves. We can have typical deprived urban areas, we can have atypical, but are semi-formal, like they have services, but they're missing quite a lot of them. They have a lot of different, they have a lot of variance when it comes to their built-up density, the population living in them, and all of the socioeconomic follow-up. So initially, we tried to, of course, classify relatively quickly using Sentinel-2, Sentinel-1, and a lot of ancillary data, the whole city, and also having deprived urban areas there, and see if it works. We had some labels because we had a data set that was given to us by a local collaborator that had some of the locations of these informal settlements. But one thing is that we decided we did not like the binary outputs. We did not like to have a specific class. We wanted to work with probabilities. So we turned into this a deprivation probability map, because then we could see more patterns unraveling, and also could have transitional zones of areas that are semi-deprived, but where they had sort of high probabilities, but it wasn't too high, but it wasn't too low either. But we cannot really disentangle by looking at a map like this. At the same time, this is a bit more, it leaves space for uncertainty to be there. And it's less, in a way, stigmatizing. And I will talk a bit about the geoethics part a bit later of when producing data that are assigning socioeconomic profiles to people that live there. This is not an easy, we're not talking about, let's say, mapping biomass or mapping trees. We're talking about something that attaches some ideological connotations behind. So we should be more careful with that. We also tried to go a bit, once we had these locations, we tried to go a bit further and characterize what happens within them. As I told you before, there is a lot of variation there. So one aspect that we were interested in was waste. And because there is a lot of waste in these informal settlements that is not picked up regularly by the authorities. It is usually dumped in locations or at the river that flows throughout the city. So there is a lot of issues, what have to do with health outcomes as well, infections, diseases that can come by the extreme pollution of the river by waste. So initially we used some very high resolution images, and we saw that we could map the waste, which on the left map with the purple color, and we could see that we could in a very detailed manner pick up this waste across the river, even very small patches of it across the informal settlements. We could even map other stuff like the vehicles, and this is not even, we're not yet to the deep learning part. This will follow a bit later. This is just with supervised machine learning classification using standard algorithms. And once we process this, we could have, this is the slum of Mathare in Nairobi, we could have a nice map of a density of waste. And as you can see, it clearly follows the river. Most of it is dumped there. And this can be vital input for authorities who are looking to upgrade this area, and they want to find the hotspots of how to organize the waste collection when this will be implemented. So far, a big part of this is happening voluntarily. The residents are self-organizing, and they are collecting and removing large parts of the waste themselves. So once we had this additional look into these areas, we could also go into create some sort of first deprivation profiles. We could see what categories pop up if we use, let's say, some simple unsupervised clustering in these areas. We'll have some specific categories, and some came out indeed. We could have locations that have a lot of water body and a lot of waste piles, or others that have other characteristics, medium building density, little to low vegetation, some waste piles, etc. These are the profiles, the archetypes, some examples of them, of what we mean by different or intra-variation of these informal settlements. And then we could also map them again and show the similarities between the different informal settlements within the city and get a better understanding of how these slums evolve or exist in the urban fabric. There is also other things that we did. Another part when we talk about socioeconomic aspect is trying to measure wealth. And this was done in Dakar here, the capital of Senegal. And well, for labels, we use the demographic and health surveys. They're global, standardized annual surveys that happen across both rural and urban areas. And they measure hundreds of indicators. Some of these indicators are compiled into what they call the household wealth index, which is essentially an asset combination based on the quality of the housing, the energy that the sources that they use, and for example, heating type, etc. It's an asset index to an extent. So having this sort of georeference, because for privacy reasons it is quite displaced, we try to connect these locations and the wealth index values with land cover and land use information, and using it as input to a machine learning algorithm. This was a random forest one. What we find out is that the models were pretty decent, but also if we extract the dependency plots, the partial dependency plots of the algorithm and the predictors against the wealth index to see the interactions, they could make to a big extent some semantic meaning. For example, we had also mapped the swimming pools there, right? If you see it's figure F. And what we see is that once the proportion of swimming pools increases, then we'll have a big bump on the wealth index. If we talk about the low elevated buildings, after a threshold, when the proportion of very low elevated buildings is very dense, probably it's a proxy for slums or informality, then the wealth index goes down. The same with the street blocks that were classified as deprived in our land use classification. Once they start increasing after basically almost zero, once they get picked up, then the wealth index also bottoms down. So this is very interesting to see also by using machine learning, because it's much more common to see that by traditional statistical techniques, but also just by using the nonlinear dependency plots, we can get a good understanding of these interactions. Yes, sure.
What's the difference between blue and black here?
Oh, the blue is just I think it's the lowest trend, just to smoothen up the relationship. So it's not it's just to smoothen up the trend a bit and make it a bit more maybe readable, but nothing new. If we predict our model that we in Dakar into the different census units and we compare it with some census data that we had, of course it's not the same because our predictions refer to the household wealth index of the DHS surveys, and we had our own, let's say, census wealth index, which is more robust but still different. What we could see is that the correlations are quite high. The patterns are captured, and I think we got a correlation ranging between 0.4 to 0.60, so a modest correlation. But it was very positive to see that by doing that, just by simply capturing land cover, land use buffers around these locations, we could get very interesting information and create I wouldn't say a very powerful model, but good enough to show that there is potential there. So moving on, another part that I would like to talk to is epidemiology. A large part of my doctoral work mostly was on malaria risk. And it was malaria risk in African cities. Now, malaria is an infectious disease that is caused by the Plasmodium parasite, and it is transmitted to humans through mosquito vectors of the Anopheles genus. And it has been impacting, in particularly sub-Saharan Africa, a lot for hundreds of years. And in particular, in the last decades, we have the average the death count is about 400,000 deaths annually, and most of them are children under 4 years old. And most recently with the COVID pandemic, due to the disruptions on the supply chain, these fatalities increased to about 700,000 according to recent estimates. So it is a very big burden for the population there. But there has not been much research on it on cities because it used to be, and it still is, primarily a rural disease because mosquitoes breed mostly on water puddles where there's a lot of rainfall. And it didn't used to be so much of an urban issue, but now with the huge urban transformation and the population growth in the cities, malaria has been increasing also and making its appearance into big urban centers as well. And the heterogeneity of intra-urban malaria risk has not been captured at the big initiatives that are happening, nor the hotspots and variations within the city have been accounted in the models so much. There has been steps, but there's still a lot of work to be done there. The increase of urban agriculture, irrigation systems, and construction sites has unveiled a lot of and given a lot of space to mosquitoes to breed uncontrollably in some cases, and then help with the transmission of the disease throughout the city. So one part we did is that, again, we used all of this information, population data, we have satellite images, land cover, and land use information, along with some malaria surveys. So a few geolocated locations across a few cities where we had the malaria prevalence as the label, as you would call. How many of the people measured in a survey that had parasites, traces in their blood. And we put them again into a machine learning algorithm, and we try to predict across the city and see if we could pick up the hotspots. And these hotspots, where would they connect with? So as we predicted our model here at about 100-meter resolution, one thing that we could see is that quickly pick up informal residents again. So the first finding that quickly we could say is that even though it's a biophysical, it has strong biophysical components, it also picks up socioeconomic effects. Why is it more prominent and high, the malaria prevalence itself, in informal residential settlements? Well, people there have less capacity to deal with the disease. They might have less access to anti-malarial medicine and drugs. They might use less bed nets, or their locations might be closer to breeding sites. For example, if we check the agricultural areas in the figure above, we see again there's probably more irrigation there, more puddles of water for mosquitoes to breed. Again, the model picks up these locations very well. And even if we check these locations, we check the street view, for instance, of Google, this is an area that has very low prevalence. We can very see it's an affluent area in a more of an uphill, because elevation plays a role as well. The higher the elevation, less mosquitoes exist. And then that's another area, more downhill, where the settlement is informal and it picks up a high signal of malaria prevalence. Again, similarly, the previous image was in Kampala. This is in Dar es Salaam in Tanzania. Model showed very similar characteristics. Again, hotspotting the informal residential areas as hotspots of malaria. And again, an affluent area there and a non-affluent and informal settlements, if we look a bit more on the 3D dimension. So we could interpret this a lot more than what we initially thought. Now, again, if we check the dependency plots, we have the high density residential informal settlements increasing, having a very positive association with the malaria risk. The planned residential areas have a negative one. And what is important to note is that the model captured about 40% of the variance, right? So it wasn't this extremely highly predictive model, but when we're talking about something that is influenced a lot by human decision and human behavior, we were happy enough because we know we have a lot of missing variables, and we know that there is a lot of things that we cannot capture, in this 2D fashion. We need to have mobility data. We need to have much more. And if we have them, then the model could be more predictive as well. And in Dar es Salaam, again, we had similar patterns. The distance to wetlands showed a very interesting effect. As the distance increased from the wetlands, the risk went down. And again, the highly dense built-up areas, the proxy for slums, had a very strong association, or the proportion of water around these malaria surveys. So it is very interesting that by using machine learning, this was a random forest algorithm. Again, we could get predictive models, but at the same time, have some input on the interaction of these variables. Because if we could use a standard statistical approach, the predictive capacity would not be so high. So we wanted to have the best of both worlds to an extent, get some interpretation of the model, but also have good predictions so that it can be used, for example, for improving malaria surveys and the design of malaria surveys and the sampling. And we applied these models at the citywide level. As you can see, we have maps, and we aggregated the malaria prevalence at administrative units so that they can be more easily ingested and interpreted by local authorities, so that when they do their planning, we adjusted them for local population patterns. So we were very satisfied with the outcome of this experiment. We had these results for 4 cities, and hopefully we will keep working on more cities in the future, and ideally not the capital and big cities where most of the data are, but more of the smaller cities, so that we can prevent situations like this arriving.
Stefanos, one question, if I may.
Sure.
So the previous models are basically you're creating those maps, or they are existing those data in terms of prevalence of malaria prevalence, and then you use line cover and land use, right? To
yes,
basically fit I guess like a random forest or something like that, to see which of the variables are able to.
Yes, exactly.
Okay, yeah. So that's like the pipeline.
Yeah, so we have this. We have a few malaria surveys that are geolocated. We take a buffer about 1 kilometer around them. We extract the proportion of land cover classes and land use classes. We train a model, and then we predict the model on the whole land cover, land use, let's say, area, and then we get this malaria risk prevalence map.
Right. Okay, I see. And so would it be, I mean, this is like purely associational studies. Can one think about doing more of a causal inferential approaches to really home in into the part of the variation that is unbiased, or at least there's no confounding that would be able to explain away these associations that we see? Have you guys thought about that path?
Yes, I mean, we had a lot of ideas regarding the methods for that. I think our main limiting factor was the malaria surveys themselves, because it was a bunch of surveys that were coming from different sources. Some of them were just taken from different papers of different scientific agencies, but were not standardized together. They were very inconsistent. Some of them had to be manually digitized. So I think it was a point where you have something that gives you a signal, but if you go into some more complex model, you will end up maybe lost, because the data themselves are the biggest problem. So in case, if we had more data and more robust training data, then I think we could do much more with the modeling approach for sure.
Right. No, that makes sense. I mean, another way to think about this, and this is, maybe down the line for a conversation, which is to think about natural experimental settings where there's some random variation that helps you, at least capture some local causal inferential parameter of interest, which would alleviate the need for covariates, because you're finding a good instrument, essentially an instrumentation that helps you identify the causal effect of interest. So that would be maybe a line of research. But please, yeah, I'll be happy to take. So have you thought about that line of
Not yet, but we can take that afterwards. Actually, I'm interested in that. Yeah, sure.
Okay, great, thank you.
Okay, so going to the last 2 parts of this presentation, this is about population mapping. As I mentioned before, given the big census data gap, we actually don't know how many people are living where in some cases. All of these estimates that the UN and the World Bank is giving is for the most part, or for large parts, projections. And there is an issue here. There is global products available, WorldPop, Landscan, that give us population patterns, how many people live in, let's say, a grid cell of 1 kilometer or 5 kilometers. But when it comes to fine scale data within cities, we have issues, especially if a census is missing. This is an area in Dakar again. And if we take one of the global products, very often we will see a pattern like this, like nothing particularly great, I would say. It's still useful, but what we were looking for is something like this, something more detailed that can very accurately capture these population patterns, which population patterns are crucial, for example, if we're talking about epidemiology, about malaria risk, about vaccination campaigns, about how many people are impacted by natural hazards, flooding, earthquakes. So population data is like the fundamental layer of any serious analysis that tries to go deep into urban sustainability. We need the exposure, how many people are affected. And in many cases, we don't have this information. Again, satellite data are very useful here. So we try to connect satellite data, land cover and land use, and to build population models that can show us these differences between informal settlements and formal settlements. And again, this is an issue, what I'm talking about, that in the informal settlements, even if recent census data are available, we can have very big mismatches on official measurements and reality. This is a bit of a political issue as well, but we see here in a slum this is not sub-Saharan Africa, this is in India. The actual population of this slum in the red line is 800,000 people. What the census says on the yellow box, that this area contains 454,000 people. So you can see the extreme mismatch about how many people are actually missing from official estimates. They are masked out from what we know. And again, this is where we go a bit more into the deep learning part. So we're trying to think of, can we create an algorithm, a deep learning algorithm that takes an image patch as an input and predicts population estimates based on the patterns of the image. And we went into an experiment like that, see how far we can go by using deep learning there. And we started with Dakar, where we have a good data set there. We have a local census that is good. We have a good gridded population to use for labels, the last figure on the right. We have Sentinel images, we have very high resolution images, and we have also Google's building footprints that were also available at the time. And we tried different combinations. What we found out is that Pleiades, which is a very high resolution satellite, of course, gave us the best fit in the data. Each point represents a grid cell that predicts population. But also Sentinel-2 data, at a much coarser resolution, the 10 meters, they were quite predictive. Even building footprints by themselves were very predictive. And if we could combine building footprints as a very high resolution, let's say, piece of information, because they're building footprints, with Sentinel-2, which gives us a bit of more of a rougher resolution, if we put them together, we get an even better result, good synergy. So the thing is that in Dakar, okay, if we have a lot of training data and we take them all from a case study and we apply it again on the case study, even if it's, we have a testing and validation and training data set, it's still the same distribution of data. It works well and we're happy, but this is not really how we solve our problem. What we want is to take a model trained in Dakar, for instance, and then apply it in another city where we have no data. Let's say Dar es Salaam. How well this model will work there. And then we were trying to figure out, of course, if we just train a model and the remote sensing, Sentinel images in Dakar, and we apply it in Dar es Salaam, it's completely different. The model, of course, did not work. The building patterns are different. So what we came up with is that we use a consistency-based domain adaptation architecture. So basically, it's two channels. One takes the Sentinel-2 data, and the other takes the building footprints. And then it checks their consistency, because the idea is that the building footprints is an invariant, is a domain invariant feature. It's where people live all across the world, let's say, in very simple terms. So it helps the Sentinel-2 image to create Sentinel-2 based deep learning futures by being used as an anchor, let's say. And once we did that as a domain adaptation approach, and we applied our model in Dar es Salaam, the results were much, much better. We got very high fits, and we used absolutely no local data, population data, or labels in Dar es Salaam. We only used the data we had there for validation. So that was very interesting from a novel perspective that building footprints can be a key actually to create large-scale generalizable population models all across the world. And more or less we knew it, but it's nice to implement it through a deep learning approach. Now we're also working with a temporal growth mapping. So how can one train deep learning models to predict across time, even at short intervals at 4 years? So this is Kigali. And we had 2 population snapshots, one in 2016, one in 2020. And we used, again, a dual channel network. I will not go into the details. Probably I cannot explain all of them right now, or at least in the time I have left. But it's a temporally based consistency network again, and it works quite well. Now this plot shows how well it can predict the growth or change, either negative growth or positive growth. So we were quite happy with the results as well, because that's also a big bottleneck in the population community, the temporal predictions. We want something that can be near real time, consistent. If there is a sudden change or settlement displacement, we can put this into the network and we can get a reasonable estimate of how many people have changed or affected in a way or have moved away. One more thing that I would like to talk about is citizen science and AI. And this relates to deprivation and how we use deep learning. So what we realized is that ourselves, we were very limited when it came to how we can create labels for models that have to do with socioeconomic, let's say, characterization, such as deprivation. And what we tried to do is to come up with an experiment so that the residents of these areas can create the training data. That's more inclusive, and it's actually more accurate from a scientific perspective as well, because these people know what is deprived and what is not, because they live in these areas. So what we did in Nairobi in Kenya again is that we cut out about 2,000 image patches, and we asked people to do pairwise comparisons between a couple of them, 2 images of them every time, and say which one of these 2 they would prefer to live in. What's the best place to live or the worst place to live, like more deprived or less deprived. And we extracted several grids like that, several image patches, and we created an application so that they could do it themselves. What is the best place to live? And they would just pick one of these 2 images. And in order to create a ranking, we use the TrueSkill algorithm from Microsoft. They use it for video games, for Xbox, for doing the player matchmaking. So it's a quite robust algorithm. And it also allowed us to reduce the number of necessary comparisons to create a ranking, because if we would use the natural formula, we would need over 2 million comparisons, 2 million votes. But if we would go with TrueSkill, we would need about 1 million votes. And we use different steps. We check the consistency of individual users, the consistency of group agreement, and also doing some random selection on about 150,000 votes. And by doing these experiments, we came up with a ranking, a deprivation index, let's say, which we used as input to deep learning algorithms and machine learning algorithms, along with land cover, land use, and satellite image data. So yeah, on the first column, we see the citizen science experiment, and we did the pairwise comparison, and we derived the deprivation score from the TrueSkill algorithm. And then we used this as input to deep learning models that just use image patches from satellite images, but also a standard machine learning experiment where we use the land cover, the buildings, always OpenStreetMap data, Google buildings as training and input to the random forest, SVM, XGBoost, more standard algorithms, and to see what works best. And this is a sample of the input of to these experiments: satellite data, land cover, land use, etc. And what we came out with is that, well, the deep learning models, and in particularly, in our case, a dense net that was pre-trained, using both the visible, but also the visible and the near infrared channel of the satellite image, gave us very good scores, predictive scores on the validation set, 0.84 or 0.78, while even the best machine learning experiments stopped around 0.7 when it comes to the R-squared and, of course, the consequent error metrics, which was very interesting from not so much about the deep learning part outperforming the machine learning, but about the labels themselves, which were created through citizen science, gave us such a good connection with deprivation through a deep learning algorithm. That was really amazing, and it shows that there is a lot of potential there on how we can include people when it comes to the responsible use of AI, and not something biased that we might think that, you know, it should be like that. And then we predicted the citizen deprivation score across the city, and it shows quite some interesting variations even within these informal settlements, which is really interesting and then warrants further work to understand why. So to close up this presentation in the next couple of slides, there is a lot of challenges so far with using AO data and coupling them with AI methods. We need well-thought approaches, we need scalable approaches, we need transferable approaches, we need to understand the local context, we need clear protocols. All of these are missing when it comes to socioeconomic mapping, because it's not so standardized as, you know, doing, let's say, physical mapping of the environment. So we are working on that. But what is clear is that it requires a lot of communication with the people that are affected and we're talking about. There's a big part on privacy as well, on the geoethics of this. How should we disseminate this data? And we did some surveys on that, and a lot of people think that, you know, just having a graded slum probability is pretty good actually, and it preserves some sort of the privacy while still giving enough information that can be used for planning and better understanding what is happening. But we should be also very aware of this, that we are using sensitive data, and we, you know, as a colleague, Richard Sluza, says, whatever puts people on the map can also take them off the map. Who is going to use this data? How are these data going to be used? We should be responsible on how we share them, who we share them with. There is cases, for example, of evictions, you know, authorities come and overnight they might demolish a whole slum, and overnight 100,000 people are without housing and on the street. And we do not want to have this data used for such purposes. So this is something very important for practitioners of the field. Another part is bias in deprived urban areas. You know, I talked about Google building footprints, and there's Microsoft building footprints as well. You know, these big companies, they're quite into this, but because they're global products, they're very biased on, you know, as they're trained on non-slum elements. So when they're applied into slums, sometimes they have huge gaps. Now, when we use a product like that, for instance, that is missing all of this density, and we use it as input the population map or something else, or exposure or connectivity, then we're missing out most of it. So sometimes we actually do more harm to use products like that, unless we are quite sure that, at least in these areas where we want them to work, they are consistent. And these products will get better, I'm sure about that. It's a matter of time. But we should be aware about there's quite a lot of bias in this domain, even if the algorithms are amazing and scalable and huge, there is still quite some issues there. And again, when we predict models about, for example, if this area is a slum or if this area is deprived or not, we should think about the stigmatization. What is it better, to have a false positive or a false negative? And there is no clear answer to that. I mean, geoethics is a field that has, you know, really sprung up in the last years. And there is people who are trying to find answers to that. I haven't found one yet myself. But again, it is something that we should be very aware of when we use deep learning, machine learning, and AI, and Earth observation data for such applications. So to conclude with, we should also democratize access to this kind of data. We should make them as much documented and readable. We should support the FAIR protocol, and we should really include the community again when it comes to the process. It should be more bottom-up than top-down in the end. And with this, I am over, and I thank you very much for your patience, and I'm very open to questions.
Thank you so much, Stefanos. Do we have some questions from the audience? Perhaps I can chip in a quick question first. So you mentioned in the first few experiments that you were using random forests and perhaps some support vector machines. So then you didn't have the satellite images as input, but you had more information about the buildings or features like that.
Yeah, it was mostly. I mean, we could have. But it was mostly derivatives. It was derivatives of the satellite data. So it could be the land cover derived from the image, the land use derived from the image, or textures, or the co-occurrence matrix. Of course, you can also include the images themselves, the spectral values, but it's not really so much of a help, at least if you're using non-deep learning approaches. That's my experience.
But then these land use features, were they extracted using a deep learning model?
No, so it was a supervised classification, like a random forest to transfer the pixels to the land cover. And for that, you have to use the pixel values to an extent. And then you have the land cover metrics as input to a land use model. So there's a lot of error propagation. You say, you go from a model input to a model input, and sometimes it's nicer to just have an image paths directly to a deep learning algorithm. You skip a bit of the error propagation there. But at the time, we thought that it would be the best approach. I think if we would do the experiment now, 5 years after, it would probably go straight away to the deep learning, although it would cost a bit of interpretability, I would say, because it's nice to know, why the land use is affected by this type of land cover, etc. It's, a bit more rich on a knowledgeable sense, I would say.
Of course. Adel?
Thank you again, Stefanos, for this these intriguing applications and presentation. So one question about the size of the data. It seems like several of the models, especially the deep model that you used, was focusing on one country or maybe several countries. Can you talk a little bit about the size of the data? That's question one. And also perhaps the domain adaptation feature, if you could talk a little bit about how that was done, a little bit more about the details, if you have a little bit time to do that, and perhaps if you want to come back to the causal inferential question as well, but that's my list of questions for now. Thank you.
Sure. So for the population data, it was 3 countries that were involved, cities from 3 countries. So we involved Dakar, which is in Senegal, which we trained the model, and then we applied it in Nairobi, in Kenya, and also in Dar es Salaam, in Tanzania. So we had an overall of 3 cities, and that's for the domain, let's say, transferability. When I talked about the second experiment on the temporal growth chains, it was only done in Kigali. So it's quite a few cities, and the population data that we had to start with were coming from census data. So this was our starting point. We had satellite images and we had the building footprints. And the idea was, again, that we have some sort of semi-supervised. So what we have to do is we train the model in Dakar, and then we also parse, let's say if we want to predict in Dar es Salaam, we parse unlabeled images in Dar es Salaam as well. And then we have the building footprints, and we make predictions. We have the building footprints and the Sentinel-2 image in Dar es Salaam, and we're checking the consistency of the futures. We have a paper on that. Maybe I can send you the paper as well. Yeah. So what the consistency does is it checks how much let's say the futures from the Sentinel deviate from the future from the building footprints. So it kind of tries to tie them together, because we know that the building footprints are the reliable source. It is a domain invariant future, so it kind of drags, let's say, the other city to fit into the building footprints. But for that, we need to have building footprints in Dar es Salaam as well. It would not work otherwise. Yeah. And the good thing with that is that once this model is finished, this approach, the training is finished, we do not need to have building footprints to predict with. We can only predict with one channel, with the Sentinel-2 image. So if we want to predict at a different age, we can still use it. That's as simple as I can. Yeah. Not being a deep learning person myself, but I think if you read the paper, you would probably have a better understanding yourself. Now, talking about the differential part of the malaria, again, I think it's if we get on our hands a big enough, a solid enough database of malaria data, I think it can be a step to do that. But I think it's mostly you. I would invite you to tell me actually what you would suggest in that. Otherwise, I would not be able to help much with your idea.
We have. You mean for the malaria one, or which one?
Yeah, for the malaria one. Yeah.
Yeah. Well, I mean, we have actually similar. It's not for predicting malaria, but doing causal inference with images with malaria using a causal inferential approach. But perhaps I can reach out, afterwards, and we can talk a little bit more about it. And also that relates to the causal inference question, but that's something maybe we can take offline.
Yeah.
Thank you.
I have a question also. Thank you, Stefanos, for a very interesting talk. I was curious about the citizen science-based data collection that you did. On some slides, you showed something that looked like street-level images, and sometimes it showed top-view images. So what was the pairs that they looked at? Was it top-view or was it street-view or both?
That's a good question. So our idea was to involve both street-view. Although we have a few examples, it was primarily, I think, wholly top-view, just looking from up top, which was also even more interesting because, to see that people that are not really familiar with looking at satellite images, they can still find the differences quite consistently. So
because I was also interested in if you would have done both, it would have been interesting to see if they do the same guess for like street view versus the same at top view. And also similarly for the machine learning models, I mean, if you would train machine learning on top view patches and do the prediction versus if you do it for like street view patches, do the machine learning models sort of make the same guesses of this deprivation depending on like the perspective of the model? That would be
that I agree. And I think the plan is to at some point finish this because we have some of the data. We just need to, as you said, do these comparative experiments because indeed it's very interesting to see what is the level of similarity in the predictions with these different modalities.
Yeah. And maybe one more question is related to this domain adaptation that you were talking about. For example, between different locations, how we can generalize the models. But another sort of axis in which you can do domain adaptation, I guess, or like at least task adaptation is that you could pre-train the models on some tasks and then do fine-tuning for other tasks, like is common in deep learning. So I was just curious, have you tried to transfer models that you have trained for some of these socioeconomic predictive tasks to other socioeconomic predictive tasks? And what have you found if you have done that?
We haven't done it yet, but what we're planning to do now is, for example, we have a deprivation model in Nairobi. And I think since it's very well trained, it could possibly be fine-tuned to predict population in slums as well, given the similarities that come with deprivation and increased people living in informal settlements. Because what is missing right now is that to have a generalizable model to predict people in informal settlements, but that you cannot use census data to train it because it's already biased. So you need to come up with a different way. And I think there's a lot of potential there with this.
Thank you very much.
All right. So I think we should perhaps wrap up here. Thank you, Stefanos, for this really interesting talk. Next week, we'll meet again, 23rd of March, and we'll have Gabriele Flud from Lund University visiting us. She'll be talking about matching and merging of structure from motion maps with statistical deformations. So it's about localization and a collaborative SLAM for 3D maps and similar. Thank you for today.
Thank you all. It's been a pleasure to be here.
Bye-bye.